right, so this next video in improper integrals, just a handful of examples, seeing how you're supposed to evaluate different integral types when we have these improper integrals. All right, over here on number 1, we got the definite integral from 0 to infinity, e to the negative x with respect to x, and here's a graph for that thing. It looks like it's of course unbounded. Is the area finite or is it not? It looks like it collapses down to the x-axis pretty quickly there, so possibly it is. All right, so then let's look at this one here, where we've got the definite integral from 0 to infinity, 1 over x squared plus 1 with respect to x. Does this one collapse down to the x-axis quick enough? I don't know. Let's just take a look here. So coming back, whoa, that's the wrong thing. This is what I want. And let's, in turn, take a look at each one of these examples. So example 3, and this is the first one. Number 1, definite integral 0 to infinity e to the negative x. Okay, what makes this thing improper is, of course, the fact that we have this obvious infinity as the upper limit of integration. We have to get rid of it. Let's replace it with a b and rewrite our integral from 0 to b e to the negative x with respect to x. Okay, so now we can just take the antiderivative e to the x, but this does need a u substitution. Why is that? It's because we have a composite function here. We've got this negative this e to the negative x. The negative x is inside of the e to the x. So we need to do a little u substitution here, making u equal to negative x, and then du would be equal to negative dx. We don't have the negative in here, so we're going to have to throw it in there and then compensate with the negative on the outside of it. Now, I'm not going to go through all of the trouble, especially when we have these improper integrals and we have this limit involved, of rewriting the bounds of integration. I'm just going to leave it in terms of x whenever I evaluate this thing. So we got the limit b goes to infinity. And now take the antiderivative. The antiderivative, this would have been something like this, just e to the u. So e to the u's antiderivative is e to the u. The negative that's on the outside stays. The negative that's on the inside is part of the du here, which is negative dx. So it's going to disappear. So I got negative e to the negative x from 0 to b. Right, you could always take that thing's derivative and make sure that you have the proper thing in the integrand just to check your work here. Okay, so now let's go ahead and evaluate. I've got the limit b goes to infinity, negative e to the negative b power minus a negative, so plus e to the negative 0 power. Awesome. Okay. All right, and maybe I rewrite this yet again and make this a negative 1 over e to the b, and then e to the negative 0, or even positive 0, would be 1. Now, I'll take the limit. As b goes to infinity, e to the infinity is super, super big. 1 divided by something super big is going to 0. That part is tending to 0. Plus 1, this whole thing is converging to 1. All right, so again, let's take a look at that graph. Again, it seemed like this one was one of those obvious ones that collapsed down to the x-axis fast enough that it actually converged. Okay, so let's look at the second one. We've got the definite integral from 0 to infinity, 1 over x squared plus 1. Okay, so improper integral. Boop. Get rid of that thing, turn it into a b, take the limit as b goes to infinity. All right, and Is this a u substitution? Should I let u equal x squared plus 1? If I did that, then du is equal to 2x dx, and there's no way, you could fix it too, but there's no way you could fix an x. That is not how we do this. Instead, we want to recognize this as arctangent. The antiderivative of 1 over x squared plus 1 is just simply arctangent. Limit as b goes to infinity of the arctangent of x. So here, your u is equal to, or your u squared is equal to x squared, so your u is equal to x, and then this number over here is your a squared, so your a is equal to 1. Okay, and then evaluate this thing from 0 to b. Arctangent of b minus the arctangent of 0. All right, in order to evaluate this, I'm just going to go ahead and draw a graph, just a sketch of what arctangent looks like in case you have forgotten. We've got two horizontal asymptotes. And then it kinda looks like the cube root function, sort of like that. Right, all right. And so for this first part, where it says the limit as b goes to infinity, the arctangent of b. So b is going towards infinity. That's this part that's over here. We're going towards infinity. And what the heck is the green graph doing? Well, this top asymptote here is pi over 2. So this thing, that part is getting closer and closer to pi over 2. And then the arctangent of 0, you can see right there, is 0, so plus 0. Well, there you go. This thing converges to pi over 2. Its area is getting closer and closer to half pi, of course, right? All right there. So let's take a look at perhaps a couple of more examples. Evaluate definite integral, improper integral from 1 to infinity, 1 minus x times e to the negative x with respect to x. So I threw this one in here because, do you recognize this as something that you're going to have to use integration by parts on it? Let's take a look at this graph here. It's a weird one, right? This is this drippy looking thing there. Does it get to the x-axis quick enough? I don't know. Let's take a look here. All right. Now, as far as this goes, let's see. Let me highlight some stuff here that I want to use integration by parts. All right, how do you even know that you have to do integration by parts? The way that I know that is that you've got some sort of polynomial equation here being multiplied by a transcendental and exponential equation. Now, our little mnemonic for this is lipit. And as far as this goes, we've got both an exponential and we've got ourselves a power. And the one that's closer over here is going to be our dv, and the one that's closer over here is going to be our, not our v, our u. So it makes sense that our u should be 1 minus x, and it makes sense that our dv should be e to the negative x. So that's how I'm going to tackle this particular problem. I've got improper integral from, we're starting at 1? Yeah, we're starting at 1 to infinity of 1 minus x e to the negative x with respect to x. And make sure I wrote that down correctly. Okay, and then we said something like we're going to let our u equal 1 minus x, letting our du equal a negative dx. So this is not like the u substitution where you have to compensate for the lack of that negative sign. We don't do that. All right. Now, let's say I let my dv equal negative x dx. And we're going to take the integral of that, negative x. No, that is not correct. It's e to the negative x. And I'm pretty sure that I've already done that antiderivative. It was the one that was, yeah, it's right there. So its antiderivative is negative e to the negative x. You went too far. V is equal to negative e to the negative x. All right, so there's all of that part, but something that I neglected to do is to turn this thing into a limit. So this is the limit as b, once again, goes to infinity, definite integral from 1 to b, 1 minus x e to the negative x dx. Okay, and now I'm going to use my integration by parts that we just saw here. And remember that the first part of this is uv. So this will be equal to, still have this limit out front, so limit as b goes to infinity of, I'm going to have this 1 minus x being multiplied times negative e to the negative x. I'll just bring the negative outside of this. Minus, and now the other part, we exchanged. Remember, integration by parts goes like this. The original one was u dv, and we're going to exchange it for the other diagonal, which is v du. That was not what I meant to do. This one here. Okay, and since, let's see, both of these things are negative, those negatives are going to cancel out. And again, this is from 1 to b of e to the negative x dx. Okay, so this is what some people do, some books definitely do, is that they remind you that this is still from 1 to b also, so that whenever we go to evaluate this in terms of FTC, the b and the 1 still gets stuck in for x on that portion of it as well, okay? All right, so now we need to take the antiderivative of this other part here. And it's the same exact thing that we did right there. Its antiderivative is negative e to the negative x, and that's going to cancel out with this negative that we already have to give us a final antiderivative of negative 1 minus x e to the negative x plus e to the negative x, and then we're going to evaluate that from 1 to b. All right, we've successfully found our antiderivative. Now let's go ahead and plug in our b's, plug in our 1's, and then take the limit of this thing. So negative 1 minus our b e to the negative b plus e to the negative b minus, we'll put brackets around this whole part here, plug our 1 in, negative 1 minus 1, how fancy, e to the negative 1 power plus e to the negative 1 power. Okay. And maybe I rewrite things to make it a little bit more obvious what is about to happen when we evaluate the limit here. So negative 1 minus b. Take that e to the negative b and put it down to the bottom. Do the same thing for this one. And then we can clean this thing up in here. So right here, all of this is just going to be 0. And then I'll rewrite the other one. I'll distribute this negative sign to it, so it'll be negative 1 over e. All right, now it's time to take the limit. All right, for this first part, I would have infinity over infinity. I'd have infinity over infinity because the b up top, that's going to go to infinity. The b on the bottom, e to the b is going to go to infinity. However, I mean, you could use L'Hopital's rule on that. However, this bottom grows faster. Since it grows faster, I don't know, that whole thing is going to go to 0. This one also is going to go to 0. Both of those terms are going to cancel out, and then we have our final answer of negative 1 over e. So our net area is going to converge to negative 1 over e. Wait a minute, why the heck is it negative? Why is it negative? Isn't this area that we're talking about? Let's go back and look at the graph. So notice that the graph is down completely below the x-axis. Since it's completely below the x-axis, the fact that it is negative does make sense, right? Anything below the x-axis negative, anything it's signed negative, and anything above is signed positive. All right. I want to say that we got one more on this video, and this one is doubly improper. Why is it doubly improper? Because you have the upper limit and the lower limit both being infinitely big, that they're unbounded. And here's a graph looking for this one, some sort of bell-shaped curve, as you can see. Okay, so what we need to do on this one is we need to pick a value in between negative infinity and positive infinity and break this up over that value. What number do you want to use? What number makes the most sense? How about 13? No. How about 0? Yeah, 0 makes sense. We're going to break it up right here at 0 and then turn this thing into two separate problems. Okay, so we've got doubly improper. And so we're going to pick a number, and it makes sense here to break this up at 0. So the way that we're going to do this is, first, before we even turn this thing into a limit, break it up into two separate integrals. What is this, 5? Okay. Example 5. We've got the definite integral from negative infinity to infinity, e to the x over 1 plus e to the 2x. Sure. And we're going to break this up as two separate pieces. We're going to break it up at 0. So the first one's going to go from negative infinity to 0. And so essentially that is, let's say, this half of the graph. Look at this coloring job. I'm pretty good at this. All right, and then we're going to break it up as the second part from 0 to infinity, e to the x over 1 plus, dx, e to the 2x dx. And that's the pink part that's left over at the right-hand side. Okay, so now we essentially have two improper integrals that we have to evaluate. The one has, the very first one, the one on the left, has a lower limit, which is unbounded. We're going to take that out and replace it with, let's say, an a this time. And for the second one, we'll take out the infinity that's on the upper limit and replace it with a b, and have two different limits that we have to evaluate. So this will be equal to the limit as a goes to negative infinity this time, definite integral from a to 0, e to the x, 1 plus e to the 2x dx. And then a second limit as b goes to infinity, and we'll take out that upper limit of infinity and replace it with a b. Okay, now we're ready to take some antiderivatives. Luckily, you know, we only have to do it once. It's going to be the same thing. It's just that the two limits, the one on the left and the right, they're going to be possibly different. We'll see what the heck's going to go on here. So let's try to use some sort of strategies to figure out how it is that we're going to take the antiderivative of this. So maybe I take a look at this and I go, oh yeah, but I've got e to the x stuff on the bottom. Maybe I've got e to the x stuff on the top. Maybe I do a u substitution. Maybe I try u is equal to 1 plus e to the 2x. And then our du would be equal to, see, this is a composite function, so 2e to the 2x dx. All right, well, you could fix the 2, but notice that what we have on the top is not e to the 2x. We've got just e to the x. So yeah, that didn't work. Instead, what this one actually is exactly the same thing. And also, take a look at the graph there. What we just did right up here. Look at the graph here. So what we're seeing here for this graph, sure, it has x's instead of e to the x. This is the example 2 here. We're just not seeing the other part of this graph that would have been over here. It's another arctangent in disguise. And speaking of arctangent, our u squared is equal to e to the 2x, and our u would just be e to the x. We do have to do a u substitution of this form, so our du is equal to also e to the x dx, which is the e to the x that's on top. Perfect. The other thing is over here that our a squared is equal to 1, so a is equal to 1. Again, it's an arctangent in disguise. It does take a bit of practice for you to recognize that that's the kind of thing that we're looking for as far as an antiderivative goes. All right, so rewrite our limits. A goes to negative infinity of the arctangent of e to dx. So it's e to the u over a. A is 1. It also has a 1 over a in front, but all of that's 1, so it's fine. And then this is going to be evaluated from a to 0, and then do the same thing for the second part. Of arctangent e to the x evaluated from 0 to b. Nice. Okay, let's evaluate each one of these using fundamental theorem of calculus. So arctangent, what a mess, get rid of it. Arctangent e to the 0 goes in first, minus arctangent of e to the a, plus, and now do the second limit, arctangent e to the b, minus the arctangent e to the 0 goes in second this time. All right, so this one a little bit more complicated because we have to evaluate the e part and then take the arctangent of that stuff as a goes to negative infinity, b goes to positive infinity. And again, it might be helpful for us to look at the graph of arctangent if we need to. So I'll just throw that graph in here once again. I like drawing it anywhere, so. I'm going to make it purple this time. Yep. There you go. All right. All right, private comment. E to the 0. E to the 0, that's going to be a 1. And whenever I go to evaluate that limit, why did I make that color? Oh my gosh, you need to stop. Arctangent of 1, sorry, I got distracted there. Arctangent of 1, I do believe that is, I don't know, someplace right over there. It's pi over 4. And then minus arctangent of e to the a. A is going to go to negative infinity. So this is e to the negative infinity. E to the negative infinity is getting smaller and smaller and smaller. So this thing is getting closer to 0. And the arctangent of 0 is 0. So I've got minus 0 plus arctangent of e to the b as b goes to infinity. As b goes to infinity, that's going to be an infinity. And this is the exact thing that we saw before. As x gets bigger and bigger and bigger, the arctangent is getting closer and closer to pi over 2. So plus a pi over 2. Okay. And then minus arctangent e to the 0. I think that we've already done that one, right? This one is the same thing as the very first one, which is a pi over 4, which is totally convenient because those cancel. The 0 is a whole bunch of nothing, and so our final answer for this one is a pi over 2. So our area, of course, like, didn't we expect this, converges to pi over 2. Looks kind of familiar, right? All right, so that's going to wrap up this first series of improper integrals where it's the obvious case where one of your bounds of integration is infinite. Either the lower one's negative infinity or the top one, the upper limit, is positive infinity. We're going to turn it into a limit. In the next video, we're going to take a look at the ones that are not quite so obvious, where you have some sort of asymptote involved, and you still have to turn it into a limit.